Um, Hi everyone. I think last time maybe, last class maybe one of the difficult class, but it's just the way that how math study will be is that from time to time we will hit some fairly difficult topic. Then um, we have to like understand and like through it a few times. So it's about like understanding and the structure, then more practice and more understanding, then kind of several repetition, you will be very good. And so, I have been like a math major and I've been doing the math. So basically math, there are a lot of difficult, you know, subjects, small subjects like calculus, differential equations, and uh, complex analysis, real analysis. So all those subjects. And initially, when you touch those subjects, it will be like totally baffled, and on like small steps. But when you practice, when you really trying to dig into it, and when you're trying to lay out the problem yourself, eventually you will get more and more understandings and it became natural. So today what we are trying to do is that first we will just expose to some like a concept called limit. So we going to the infinity, and then we trying to take number to the infinity, and then try to observe the training of the different different expressions. Then this is a relatively easy and topic. Then we will go back to our last topics and do more exercise, and we will do more um, like problem solving. So we will be able to truly understand the last topic, and you know uh, on on the higher order equation resolution, because the low order until second quadratic is quite easy. Then also the relationship between the root and the coefficient. We have been going showing the formula of the like Vieta formula. Then we will take it to the higher order, and then do some real problems. Then also, there's a Newton formula if we have time to finish that. So let's get into the topic today. And so um, first is that like limit. Basically, what is a limit? A limit is that if you have a number sequence, like for example, if you have an expression like n over n plus 1, and if you put a curly brace around it, it's just representing a infinite number sequence, 1 over 2, 2 over 3. Oh, is that I'm not sharing screen? Sorry.
Yeah.
Yeah, so I was about to understand that I was making a mistake on that. Let me begin that. Let me begin share screen. And so basically we will really, yeah. So basically a limit, for example, if you have a number sequence, for example, this is a curly brace, n over n plus 1, then basically it's a number 1/2, 2/3, 3/4, and the all the way to infinity. And when n equals 17, it is 17/18. And when you take n to the infinity, then it's quite obviously that uh, it's still going to be a number less than 1, but it's infinitely close to 1. So basically, that's the concept of the, the limit. Limit means that it's a trend, that when the like a subindex goes to infinity, what's the trend of this number sequence will tend to. So for example, this one, we actually the limit of sequence n tend to infinity is 1. So basically, this is the sign for the limit. So, and this is the trend, where the n will go. It will go to positive infinity, and that's going to be a 1. So basically, their class of the numbers can be like evaluated when, especially the rational functions. Rational functions are, numerator and denominator both are made up of a polynomial. So basically, what will happen when x tends to infinity? So it's actually quite easy. This type of the problem actually quite easy, because we actually can, for example, this is the highest power is 3. So we divide by x cubed on both numerator and denominator. We will find this rational expression, which the leading term became a constant because we divide by x cubed, and x cubed both on numerator and denominator. Then we will find that when x goes to infinity, the non-constant trailing term will be infinitely small, because imagine that x squared going to be huge, like 1 trillion and 1 quintillion. Then the trailing terms just became, you can just ignore them because they became just too small to really matter. So basically, there is a limit to this rational function, and when it goes to infinity, it just will be 3/5. So yeah, so there are a bunch of those things that we can trying to practice. For example, this one, when n equal to the, let me see if I have any. Oh, problem 88. Okay, I'm going to, yeah. And so basically, they are like limit. So this one, when n goes to infinity, and it's obviously going to 0 because it's going to be so tiny. Eventually, it didn't matter. And so not just n 1 over n, 1 over any n's power actually will be like 0 eventually. And so these are the the polynomial rational expression. Let me see. Yeah. And am I sharing the screen? Are you able to see my screen?
Yes.
Okay, yeah, I'm just wondering. And so So for example, these are the rational limits. That rational limit usually always divide both numerator and denominator by the max power. So we're going to divide by x to the fourth on both numerator and denominator. So this one is actually quite easy. So this one will be the like 1/2. And so this actually we're going to also divide by x to the fourth on numerator and denominator. Then what happens is that you will see that this term will go to 4. And this actually will be, so this limit actually will be, so this one will be 2/4. And this one is actually going to be 0 because when you divide by x4 to the, so it's going to be, x to the infinity. And then here, the leading term going to be 2 over x minus 7 over x squared plus 1 over x to the third. So this one, if I divide by x to the, so I divide by x to the fourth. Oh, this is divide by x to the fourth. Divide by x to the fourth. And oh, Telegram. And so basically, the bottom, if I divide by, for x to the fourth, the leading term going to be 4. So on the top, basically every term, 1x go to infinity, there will be 0, 0. Everything will be 0. On the numerator, it's going to be 4 is the max term. So basically this take to infinity, this going to be 0. And so this basically, we are going to divide by x to the fifth on both numerator and denominator. What we will find is that the leading term going to be 2, and the trailing term I'm not going to cover it. We'll just leave it alone because it's not going to matter. And then if I divide by x to the fifth, then basically the leading term basically it is 4 over x. 4 over x, and the trailing term is going to be even smaller when it goes. So really this term matters. And this term, when x to the infinity, divide, so basically you can say that approximately equal to this, and limit x to the infinity, and then divide by a fraction equal multiply its reciprocal. So basically it's actually is 2x over 4, and x goes to infinity. So basically this actually, x over 2. And when you take x to the infinity on the x over 2, it actually will be infinity. So these are the ways that you could do some infinity stuff. And so I think we will, get started on the so basically, I think Charles need to cover problem 88. So let's try to cover that. Yeah. So basically, last time I think most of the problem is very difficult. Let's begin to cover last time's problem. And I think let me cover number 88 first. So basically, you know, we're going to cover a few other problems. So basically, and so basically, let me trying to cover that problem. And 88. So, and a lot of those problems are not very easy. And I think let's cover this problem first. So if it has double root, you know, find p plus q. So this problem is actually a little bit advanced. It's actually the, you know, the higher iteration of Vieta formula. Let me cover that part first, because basically I think last time we did cover finding how to find the root of polynomial, but we didn't really cover the, we didn't really cover the like coefficient and the root. Let me copy that chapter over. So basically, let me copy that chapter over. So basically, coefficient and root follows a formula called Vieta formula. We actually been talking about that in previous class, but haven't been very deep. So today we are going to dig very deep into this phenomenon, and then we'll really, you know, apply into the real problem. And so basically, there's a relationship between the coefficient. This is a like a generic form for a monic polynomial expression with leading term is 1. But even more generic is like leading term could be any number. So basically, you know, if this is the format, and then basically, assume this is the format, we always can convert into a G by dividing the leading term. So basically, we actually can use the like monic format as the discussion topic. So basically, assume it's monic. Why we use monic? Use monic. Basically, it's easy to mapping the solution of the polynomial to its coefficient. So it's very easy to do it this way, because if the leading term is not 1, we can divide by leading term's coefficient to make it monic. So it became a monic polynomial. And so assume it. So basically, you know, we have been learning the you know, this polynomial and the phenomenon, and also has been going through all the like theorems. One of the key theorem you have to take away if you forget everything else is the fundamental theorem of algebra. Fundamental theorem of algebra is that, you know, if a polynomial like has nth degree, like nth degree polynomial always has nth roots. So basically that's a no fact. It's basically it take like maybe 2,000 or 3,000 years for algebra to develop to that stage to recognize of that fact. But right now we just assume that it's a given fact. that we can just use. So given this assumption, so by fundamental theorem of the algebra, because if it is a nth, like, take it more generic. Right now we are talking about the cubic root, and but you can take it to 100 root, power and even higher without any problem. So if you have a nth degree polynomial, then you will have to have that many root, and it can be written in this format. And if you are written in this format, then basically you are able to expand the product. So these are the product of the root in. So this is a polynomial nth degree polynomial in like root form. So it's a root form. So if you already given, for example, it's a cubic polynomial with 3 root. So I can write it as x minus r1 root 1 multiply x minus root 2 multiply x minus root 3. So basically this is in the root form. And in the root form, then you can expand it. When you expand it, you basically, the first coefficient is actually r1 plus r2 plus r3, but with a negative sign, because this is a negative. You can actually try it yourself. It's very easy. And basically, this is basically every term here is a binomial. Binomial is just you have to pick. For example, I pick root 1 as a factor. Then the next one I pick both x and x. So I will get a negative r1 x squared. So basically, if you pick, so basically, this is the three-term binomial. If you multiply it altogether, it has 8 terms, basically, because it's 2 multiply 2 multiply 2. So those 8 terms, if it's only taking x, that's the leading term, that's the x cubed. If you take only the root, the constant, it's going to be negative r1, r2, r3. Then basically the middle term, x squared term and x term. X squared term, basically you have to take 2 of the x as the factor. The remaining factor will be the one of the root. So basically it will be this format. Then for the x term, you can only take one x. Then the other 2 terms, basically you are picking on the different combination of 2 of the product of the 2 roots. There are only 3 iteration of those combination, R1, R2 plus R2, R3 plus R1, R3. Why they became positive? Because 2 negative multiply up to be positive. So you will find this phenomenon that negative, positive, negative. So basically it's just, depending on how many negative sign you pick up along the way. So basically when you expand this product, you get this formula. And this formula, basically from a generic form, basically, each term, if you starting from the more generic non-monic form, the coefficient basically is the result of the A2 divided by A3. A3 is the leading term. And so the coefficient looks like this, is the denominator is always the leading term, and the numerator is just the second, third, and all the way to the last term. And So basically, given this fact, the sum of the root is actually has the sum of the root. They have the negative sign. The sum of the root is negative a2 divided by a3, and the product of the root is this term, is actually is negative. There's a negative sign here. Negative a0 divided by a3. So basically, we are going to summarize this. We're going to introduce a concept called symmetric sum. So this is like a 3-degree polynomial. Imagine you get a 100-degree polynomial. So basically, if you write into like a form of x minus √1, x minus √2, and all the way to x minus √100, then what's going to happen is that the multiplied. So basically, how many terms you have? You actually have 2 to the like 100 power terms, each term multiplied out. Then you can combine them into like, you can combine those product into the 101 terms. And so the leading term going to be x to the 100, and the trail term going to be just a constant. Like trail term going to be, and trail term actually, because you have 100 root, after you multiply 100 root together with negative sign, basically it is R1, R2 multiply all the way to R to the 100, because you have 100 negative sign put together. Actually, it's going to be plus. So basically, the trail turn constant going to be flip flop. If you have even number of the solution, it's going to be positive sign. If you have the odd number of the, it's going to be negative sign. So I'm going to only observe the constant term and also the next term, because those are easy to reason and easy to understand. So basically, for the x to the 99 power, basically in this product, I'm just going to pick all the x except one of the term. I'm going to pick one of the root. So basically in this format, x99's term going to be minus x R1 plus R2 plus all the way to R100. So if you imagine that, so that's going, so the trail term going to be this way. And then 2 to the 100 is a huge number. And imagine last time we have been talking about, a woman helped to solve a king's problem and trying to get a rice on the chessboard, like box. She only needs 2 to the 64th power of the grain. So that's so basically, if you have such a high degree polynomial, I mean, it's just dizzy to look at. So basically, in the middle, some of the terms going to be really huge. And so basically, so the second term, why it became huge, in the second term, basically you are picking 99x. You are going to pick 99x, except two of those. Two of those going to be root. And because negative going to be positive, so it's going to be plus. It's not going to be minus. It's going to be R1, R2, and R plus R1, R3. Then it's actually, in fact, it's all the possible like product of two root. So it's actually we have a terminology for this. The terminology is called, the second symmetric sum. So basically, x to the 99 is going to be second symmetric sum. Then x to the 97 is going to be third symmetric sum. And third symmetric sum, imagine it's actually, it's all the possibility R1, R2, R3, then R1, R2, R4, something like that, all the way to like R98, R99, R100. So basically, it's actually, it is like 100 through 3. So basically, they are how many turns you have. It's actually in the statistics, it's 100 through 3. So this is a sign for choosing action. And so basically, we actually have so many symmetric sums that related to this is actually exactly what. So if we really just go back to see the if we go back to see the like Vieta formula. So the Vieta actually apply to the Vieta formula. So Vieta formula that for a generic polynomial of degree n's. So basically, it's the symmetric sum, the n's symmetric sum. So this is the first symmetric sum, and the second symmetric sum, that's all the possible product of two of the root. Then this is the highest, the nth symmetric sum, and is just a flip flop. So this is a starting always from negative, then become positive, then negative. So the last product, the product could be negative, positive, depending on the number of the root you have. So basically, this is the basic formula if you really care about it. And so basically, for the quadratic formula, that's basically is simplest form. This is used most, but yeah, the higher turn, you should be as comfortable as easy to use it. For the cubic form, it's R1 plus R2 plus R3 equal to negative B over A. And this is the, second symmetric sum. Then basically starting from negative, then the next one going to be positive, the next one going to be negative. So it's going to be just, flip-flop. It's just, the reason behind it is just, you pick your product, pick your turn, and how many negative sign you accumulate around the way. That's why flip-flop phenomenon shows up. And anyway, so this is just coefficient and root. Coefficient and root has this relationship, and this relationship is very important. So in one word, to summarize this, so the Vieta formula is the symmetric, the nth symmetric sum is actually the case. I will say the case. Yeah, the case symmetric sum of the root is the like -1 to the case. And this actually map, so the first symmetric sum is always like √1 plus √2 plus √3 plus all the way to √n. And the first symmetric sum of the root is always equal to like a n minus 1 over an and a negative 1 to the first power. So basically, so if you remember how the first degree of the sum, then the next one is just come very naturally because you have a next one to the, like this is k, and this is a n minus k and an. So basically, this is, it's just one next to it, one more next to it. How much more next to the leading one? So this is the last one is just product of all the root. The product of all the root will be depending on, so if you have odd number of the root, it is negative. If you have even, it's positive. So basically, that's just has a relationship of this. Okay, so we kind of get the understanding of how this formula, how this relationship is formed. And it's just, based on the product of the root form, based on the fundamental theorem of algebra. And so let's trying to do the problem. So let's trying to do the first problem is that let's trying to do this. So basically, so this problem, let's trying to do it. So has two double roots. So basically you can assume that two double root, basically it's x1 equals x2. And let me use the root one. So basically, root 1 equal to root 2 equal to, let's say, r, and root 3 equal to root 4 equal to s. So basically, this is how it works. So if we add all the root together, because this is monic, if it's monic, then basically, the negative 16th. So basically, negation of negative 16 is actually equal to root 1 plus root 2 plus root 3 plus root 4 equals 2r plus 2s. So basically, this is just how it works. And then, because here, 16, how does 16 come from? The 16 basically, this is basically, the a to the a4 is equal to 1, a3 equals to negative 16. And the root, the sum of the root is actually equal to negative. And negative 1 multiply a4, or a3 divided by a4. a4 is the leading term. So basically, this is how this expression comes about. Then basically, the symmetric sum. So if you have R1, R2 equals R, R3, R4 equal to S, how many symmetric sum could you have? So basically, if you expand it, all the possible way is that symmetric sum is R1, R2 plus R3, R1, R3 plus R1, R4 plus R2, R3 plus R2, R4 plus R3, R4. So basically the symmetric sum, then because of the flip-flop nature, actually going to be A2 divided by A4, A2 here, is actually 94. And A4 here is just 1, so equal to 94. And then we can plug the value here. R1 is actually R, so this is R. R2 is R, also R. So this is R. R3 is S, and plus R1 is R. R4 is S. R2 is R. R3 is S. And R2 is R. R4 equals S. And plus R3 is S. R4 equals S. So S, S. So basically, if you multiply them together, I got, R squared plus 4RS plus SS equals 94. So this is the polynomial. So this is, why this is 94. This comes from here. So basically, so from the coefficient of x squared, we actually got the sum because it's a double root. So basically with the double root, we actually got this. So this is equal to 16 and R plus S going to be 8. And then basically R squared plus 4RS plus S squared basically equals 94. And then we actually is able to solve for example, like we can solve for R, for example, let's say R equal to 8 minus S. Then we can plug that back in. And also, let's see, it's trying to find P plus Q. So basically, P plus Q here is actually, so P basically is going to be equal to negative. P is the third term, so it's going to be a negative. The symmetric sum of the root. So basically it's R1, R2, R3 plus R1, R2, R4 plus R1, R3, R4 plus R2, R3, R4. And because, so this is the symmetric sum is equal to A2. So basically P is actually equal to like A A1 over A4. So basically is equal to negative of this term. And this basically you actually is able to plug in. Let's say that, we can check R, so this is R square S plus R square S plus R, and this is S square plus RS square. So basically, it's possible to do this, and we can say it's negative, and we can factor out RS. So RS, and then this is like 2R square S plus 2R S square. So basically it's R plus S and 2. So basically, if I multiply them back, it should be able to get those. So basically, given, so is this type of the problem? So usually, there are two ways of solving it. Given the symmetric nature, so a lot of time you don't really have to solve it out. So basically, we know that, R plus S equals 8. And then we only need to know the RS. So basically, this is actually R plus square plus 2RS plus S square, then plus 2RS. So basically, this will create a product equals 94. And this part basically is R plus S square plus 2RS equals 94. And R plus S equals 8. So this part is actually equal to 64. So 64 plus 2RS equal to 94. So RS is actually equal to 15. So basically, this is where the RS equals 15 come about. So basically, right now, we know that RS equals 15 and R plus S equal to 8. So it's possible to calculate the P. So P basically is negative to RS. I'm going to, because negative to RS, I'm going to just put in RS equal to just 15. To multiply 15, multiply R plus S equal to 8. So basically, that's going to be negative 30 multiplied this going to be negative 240. So that's the way you actually find it. And then we are able to find a P. P basically is much easier. P is actually just, continue upon the symmetric sum. So basically, P is actually equal to root 1 multiply root 2 multiply root 3 multiply root 4 equals to, because root 1, root 2, it's actually, R square multiply S square equals RS square, because RS, we already know it, it's 15, so it's 225. So basically, P plus Q basically is just these two numbers add. It's going to be like, P plus Q going to be equal to negative 240 plus 225 equal to negative 15. And Charles, does this make sense to you?
Oh, yeah.
Yeah, so basically, this is actually, this actually is very typical. If you go for computation, this is a normal level of the problem. It's not difficult. This is not considered difficult. It's just simple application of the Vieta formula. So the Vieta formula actually does go higher than, second degree, because you only will touch the Vieta formula, like things like it's only limited to quadratic, but in fact it's not. It's very generic. And the Vieta formula, actually, you can even argue that, like, the first degree is also the Vieta formula, because if you just write it in the generic form as like, ax plus b equals 0, this is actually a generic format for the linear. So basically x in this format is going to be negative b over a. So negative b over a actually is true even starting from the first degree, if you put all the term, including the constant term, to the left side of the equation. And so this is the symmetric sum of the symmetric first degree sum of the, of the solution of the polynomial, even starting from the linear. It's already applied to the Vieta formula. Then from the second degree, it's quadratic. Quadratic Vieta formula is actually maybe a special chapter on the quadratic equation. So basically, a lot of book writes that way. But take it to the higher degree, it's very natural. It's very, very natural. So a lot of time when solving this type of problem, especially, if they are not like, I will consider like fifth, sometimes even sixth root as still feasible to write it out fully. If you write it out fully, you help yourself to understand the meaning of it. Then basically, given the limitation, so basically the limitation here is two double roots. So basically, R1 equals R2 equals R. So basically, when you write out the, symmetric sum, then fill in the limit factor, then it's possible to write it out correctly and also apply it. So that's the way that, okay. So I think let's kind of, let's go through last time's homework a little bit. I just want to spend a little more time on it, because this is, again, this is still a difficult, like, subject, and difficult topic at this point. Just want to show you that, how are we going to deal with it. So, find the remainder. So this is the one of the practice on the back of the book. Find the remainder of x to the 13th plus 1 divided by x minus 1. So basically, typical way is that there f1 equals 2. So basically, you are able to find out the remainder of the quadratic equation. If you this is just a proof that if you really want to divide it, you actually can use the this is called synthetic division. It's extensively used in dividing polynomial by a linear binomial. Linear binomial is like x minus certain thing. So basically x plus or minus certain thing. So basically, if you really do it, the remainder is 2. But do we really have to go that far by doing in this format? The answer is actually no. So basically, you actually is able to like just fill in one as the function evaluation it will get to. And why? Because when you divide a polynomial by a linear term, the remainder will be a constant always. So first the concept is that the remainder will be constant. So basically, when you divide this polynomial by a linear polynomial, and the remainder will be constant. Remainder will be constant. That means that you can fill in any convenient number to find it out. And so basically, the number at x minus 1 is convenient because this will, whatever the quotient, for example, is gx. So basically, x to the 13 plus 1 is actually equal to, let's say that qx quotient. It will be in this format. Quotient x minus 1 plus a constant remainder. Let's say remainder is r. And so fx equals, and let's say that equal to this format. And the remainder will be a constant. Since the remainder is the constant, to evaluate this, and you really don't know the definition of qx, but in order to evaluate this portion, easiest way is to just pick x equal to 1, because when x equal to 1, the whole term will be 0. So basically the remainder fx equal to r, and so the remainder 1 f1 you actually is able to plug in, and 1 to the 13th is still 1. 1 plus 1 equals to 2. So basically, this will actually satisfy this. So basically, there is, and so this actually, gave you the quickest way using the remainder. Remainder is the theorem. And so the remainder theorem could be used, or if you just brute force by the synthetic division. Another way I'm showing you is that, if you know the formula, and so if you x13 plus 1, and is actually x13 minus 1 plus 2. So basically this portion, if you know the factoring for formula, and any power, x to the any power minus 1, you could always factor out to be this way. So basically, you get a remainder 2. So that's the first one. And then finding root. So finding root, it's always a, like, always a trial and failure effort. And so for example, this problem, if you really do it, first you're going to observe is that the sign change. And so there are 3, 1, 2, and 3 sign change. So they are like, there at most will be like 3 positive. So we are kind of, and then we will also trying to plug in the negative one. We will get like, let's say that g negative y will be 2 to the y4 plus 9y cubed and plus 14y and minus 6y minus 63 equal to 0. So basically, it will have 6 positive and 1 negative. So basically, by judging the sign of the coefficient, you can guess how many positive and the negative. And 3 not means that it's always 3. It's always like 1 or 3, up to 3 positive, and it has up to 3 positive solution and up to 1 negative solution. So that's what you are here to looking for. And then you see that one G0, when you plug in 0, that's going to be negative 63. And you also can plug into a very big number, a negative number. For example, if you plug in negative infinity, basically it's going to be positive. So you know that it sure will have a negative solution. And so if it has so basically, I was trying this. I tried and it succeeded because at 0 it's negative, and at negative infinity is also negative. Then you can try a few number. Then for example, if you try -2, you actually will find out it's going to be positive. So basically, you can narrow in several times, kind of just try different numbers. You will be able to solve it. When you solve one, get one root. When you get one root, then you are able to divide the second one, and then yeah. So I think the first root I did find is actually 3. So 3 is actually on top of here. And so when you learn the synthetic division, basically when you evaluate the function, you actually you don't have to fill in each number. You just use the synthetic division, and the remainder going to be the function evaluation result. So basically, the first I tried 3, then after I get 3, then I also find out there's a negative. So you will be able to know that there's at least one positive. So here because G0 equal to 0, and you also know that G negative infinity going to be positive, and G positive infinity going to be positive. So basically, or G0 equal to negative. So basically, based on the sign change of the function value, you are very sure there's at least one real positive and one real negative number. And then basically, one after you get those facts, the remaining thing is by assuming the, like, when you're trying to assume the possible solutions by factoring those leading and the trailing coefficient. This is the leading coefficient. This is the constant term. So basically, there are combinations like, 3, 9, and the 7, and like 21 and 63. So those are the integer terms and also need to be divided by 2. So basically these are all the possible ways that you can try. So if you try a few, you figure out, especially usually you try from the small number, and like 3 basically is the smallest integer, and you can also try 1. So basically 1 you're able to rule it out fairly easily. So the next turn you try is 3. 3 is actually you get out fairly easily. Then after you lower degree, you begin to use the new set of the coefficient try the negative value. And the negative value basically, it's also easy to figure out because like -3 is the smallest one, that integer, you will find that, it's still positive. Then basically you will try the next one with a fractional solution. Then after you divide until here, then basically it's became a quadratic. You are able to apply the formula. So that's the way to solve this type of the problem. And yeah, so so this is the problem 86. So find all value of m, which will make m plus 2 factor of this. And so this is a factor only one f -2 equal to 0. So we kind of plug in. So f -2, so -2 to the third plus 3 multiply m square and -2 square plus m and -2 plus 4 is actually going to be equal to 0. So basically this is where we, this is negative a plus, 12m square minus 2m plus 4, so equal to 0. So this is where this comes from. So this will be a factor only at -2, when x equal to -2, the whole thing will be 0. And so if this is 0, so basically we are facing with a quadratic equation, and the quadratic equation is actually fairly easy to solve. So basically, if we simplify it, it's going to be a quadratic equation. And then we are able to solve it. Yeah, so the next question is find the product of the nth root of 1. And nth root of 1, for example, the first root of 1, obviously x equal to 1. You can do a few examples. X squared equal to 1, obviously you actually have, positive -1. X cubed equal to 1. X cubed equal to 1 is actually, nth root of product of the nth root. And it's actually in the complex analysis. So it's a more difficult topic, but basically I'm just going to, if you draw the root in the complex plane, all the root of x to the nth equal to 1 will be located on the unit circle, for example. And then basically those are the 3 roots. So this is actually, 1, 0. 1, 0 is not, so this is just, the first solution is actually x will be equal to 1 plus 0 I. I is the complex part. So here, basically, the second and the third root is actually, the x1, x2 will be actually, if you draw it out, it's actually going to be -1/2 plus square root of 3 divided by 2i, and the x3 going to be -1, and minus. So basically, actually x equal to 3 is actually still solvable. I just trying to prove this to you. So basically, it's just more impression and more understanding, because this topic may take a while to digest. I'm just going to give you a concrete example. So x squared or x cubed equal to 1, I can convert into x cubed minus 1 equal to 0. And if I factor it, x minus 1 and x squared plus x plus 1. And this is actually a quadratic equation. And so basically the quadratic equation, if you're really trying to find it out, it's actually, A equal to 1, B equal to 1, and C equal to 1. And then discriminant is actually B squared minus 4AC is equal to 1 minus 4 multiply 1 multiply 1 equals actually -3. And -3, so basically this quadratic equation don't have any real root. It has two complex root. So, but complex root is still a root. So you still have to multiply it. So basically, but it's actually, at some point we're going to teach like, the complex number multiplication, but it's going to be a little more complex. But anyway, if you're trying to use the quadratic equation to solve this, basically you're going to get two extra roots. In the complex plane, it's going to be like those three. And if you multiply it, and I'm just going to try to show you, the what the geometric meaning of complex number multiplication. And the geometric meaning of the complex number multiplication is just magnitude of the complex number multiplies, and also the angular rotation will add up. So the angular rotation of √1 is 120 degree. And the angular rotation of the second is actually 240 degree. If you add them up, it's 360 degree. And the magnitude is just the absolute value of the complex number is 1 multiply 1 equal to 1. So basically, the product of those two complex roots is actually equal to 1 magnitude 1 rotate 360 degrees, still going to rotate back to 1. So basically, the three roots of the cubic solution is actually 1 multiply those two complex number, because multiply 1 is just 1. So basically, we actually given the nature of this, and actually, x to the fourth equal to 1, actually will have four solutions. You actually is able to find out is actually +1 and the -1 as a positive I and the negative I. So basically, so it's actually in the complex plane, actually it's look like this, 1, 2, 3, 4, and it's actually, evenly spaced around the unit circle on the complex plane. And so does the fifth and the sixth power. So basically, on the complex plane, you will find fifth power. Basically, you will find it like this. It's like a pentagon. If you connect those together, it's going to look like a pentagon. But basically, it's just going to be rotate like this way. And yeah, I think since you are still in a lower grade, but I'm trying to expose you to all those things, because to tell you the truth, basically, if you had to excel in the context, contest, you do need to know those concepts. You do need to know all those details, and it's just the way that you cannot avoid it. It's actually the earlier you're exposed. We are not shooting for you guys to be excel in this contest because it's too close. And especially, if you're really trying to be good at math, you have to need patience. And just like 3 months to prepare for a contest, there's no way you will excel. But we have to draw out a plan that, exposed to difficult concept and then repeatedly go back to it, bombard it by gradually more difficult problem and get more better understanding, then eventually we'll be really good at it. I actually take me like a lot of preparation to be excel at math competition. So that's my own story. So anyway, so basically, we actually is able to easily solve the root all the way to fourth root, basically. And you can prove this because I's definition, you know, I square will be equal to -1. So basically, with I's definition, this is how I is defined, the unit, imaginary number. And then basically, it's obvious that, those 4 numbers are the root of those. So basically, you will, if you if you really trying to do it, you will find that first root, let's list a table to 1, 2, 3, 4. And if it's one degree, it's -1, or it's 1, because the only root, the first degree only root is 1. The second degree is -1 multiplied +1 is -1. And the third degree, we also prove that the product of all the root is 1. And the fourth root, we prove it's -1 because the fourth root is just 1 multiply -1 multiply I multiply -I. And if you multiply then this is -1, this is -1 multiply -I square. And negative positive is just equal to I square. I square by definition is -1. So basically, it's just flip-flop like this way. So this is not a proof, but basically just give you a more sensible feeling on, the quintessential meaning of the fundamental theorem of algebra, the nth, nth polynomial always has nth root. It will, by taking consideration on the complex number it is. And then, so the real thing is that we actually using the Vieta theorem. Vieta theorem is that the product, so the product of all the root, the product of the root basically is -1 to the, so here basically is -1. And -1 is just, it's A0 divided by AN and -1 to the nth. Because, so the formula looks like this. So basically that's the product of the order root. But because A0 is -1, so basically it's -1 to the n plus 1. And over AN is just 1. So basically, it's just over 1. So basically that will be it. So that's the That's the root, product of the roots. This is actually a fun thing to really imagine it, because I trying to display this to you, just gave you, the more background and the more context of this, because this is actually the easiest possible. This is the easiest possible of nth degree, like polynomial, because there can't be more simpler nth degree polynomial. And by theorem, by fundamental theorem of algebra, nth degree always has nth root. Then possibly a lot of people will ask that where are those roots? So, the root is actually all located, if you have a complex plane, it's all located on the unit circle of the unit circle is the circle with radius 1. It's always located on the unit circle of a complex plane. And the first root is always like 1, 0. And the second, third, and these are all the evenly spaced out and extra dot on the complex plane. And, you actually can use Pythagorean theorem. So these two numbers, the product or the power of the square of those two numbers will add up to 1. And so it's just like certain degree. For example, this is the fifth power. Fifth power, so then you will ask what's the root of those. For example, for the fifth power, basically, in algebra, especially measuring the degree, usually they don't use 360 degrees. They actually will treat the whole circle as 2 pi. So basically the degree of this, the whole circle is 2 pi. And the degree this is actually 5 dot, you divide by 5. So basically this is the degree of this angle for the first dot. And then, so then if you are familiar with the, so unit circle, you actually have to use a lot of trigonometry functions. So this one, actually the x-axis is actually cosine, 2 pi over 5, and plus sine 2 pi over 5 I. So this is actually the first non-real root. Then this is the second. Second, basically, you can write it out is actually cosine, 4 pi over 5, and plus sine 4 pi over 5 I. So basically, then this is a this is the mirror image. The fourth solution going to be the mirror image of this. So basically the cosine will still stay the same. It's the cosine 4 pi over 5 and minus the y axis will become, the y coordinate became negative from the positive. So minus sine 4 pi over 5 I. And the last number is just going to be, it's going to have the same part. So it's cosine 2 pi over 5 minus sine, because it's the image of the, so it's minus sine 2 pi over 5 I. So this is, just the way that, so this complex number system is designed to handle any degree. And it's actually quite fun imagining that how big the complex number covers, because you think that, negative, like x squared equal to -1, this actually can cover like all the roots to x to the 100 or even 1000, whatever, and unlimited degrees. And you don't have to design. So for x squared root equal to -1, it actually will generalize the whole thing to infinity. And you didn't have to, invent more number system based on x to the 4th, x to the 100s. So that's a fun thing. And then this is the rotational thing. And so let's trying to get. So today we have been. I think we will stop at here for coefficient and root, really, because this is actually the quintessential meaning for the Vieta. Vieta formula is one of the difficult things, that relatively difficult, but it's not too difficult. But you kind of just have to get used to really by visualize, the expansion of the root form and how it mapped to the coefficient. And in case you like, dealing with problem like problem number 88, how are you going to expand it and plug in and relate them together and get the answer. So it's not too easy, but you will get to use it, get used to it with more exposure. And let's see if we can squeeze in one more problem. And yeah, so this is a function, is a 7th power, and ax to the 7th plus bx to the 3rd plus cx minus 5, where a, b, c are constant. And if f -7 equals 7, find f7. So basically f -7 will be expanded out to be this one. And so here, by changing the sign, it's going to a to the equal to -12. So basically we are able to figure out, this one actually is not very difficult. So basically this one is just, plug in and you will get it. Yeah. So let me try to show you why this is the case. When you plug in -7, basically, it's just a and -7 to the 7th plus b -7. So f -7, it skips on step. I'm going to just write out the skip step so you kind of get a better understanding. And plus c and -7 minus 5 equal to 7. Then basically, given the negative sign and to the 7th, we can extract the -7 out. So it became -a and 7 to the 7th plus, and this is -1 to the 3rd going to be negative. So I'm going to, just change the sign of positive became negative, negative b, and 7 to the third. And so this is negative, I extracted out, going to be negative c multiply 7 minus 5 equal to 7. So here, basically, I have a negative sign here. So what I'm going to do is multiply -1 on both sides. And multiply -1 on both sides, I'm going to get, a multiply 7 to the 7th plus b to the 7, multiply 7 to the third, plus c multiply 7, and plus 5, because negative, negative equal positive equal to, and this is -7 multiply 1, or 7 multiply -1 equal to -7. So this is, and I'm going to -5 on both sides. -5 on both sides is a multiply 7 to the 7th plus b multiply 7 to the third plus c multiply 7 equal to, so I -7 on both, 5 on both sides is -12. So this is where this step comes in. And so basically, let's check F7, how close F7 is. So F7 basically is just, if you plug in, is just the front portion is exactly here. So this part is -12. And the constant term is -5, and then equal to -17. So basically, that will be the, the result of this. So basically, let's say that this is actually a special phenomenon called oddity of the odd function. And so let's take away 5. Take away 5. So basically, a to the x to the 7th plus bx to the third plus cx. It's actually an odd function. Odd function means that the function, f negative x going to be negative f x. So basically, a negative, odd function, it just means that, for example, x equal to y equals x is odd function. A odd function is just, if you have a negative value, it's just, for example, negative x, like f -1, f1, y equals x is a function. So f1 will be I1 and f -1 equal to -1. So basically, if I want to get the, a parameter value negated, then the only thing I need to do is negate the result value. So basically this part, so all the odd functions, these are the odd power function, odd power, and x is odd 1. These are odd power function. It's add together a combined function. It's going to be odd. For me to want to get a negative, so this part is odd and taking away it. And so basically, if I take away 5, this part, basically, if I have a gx equal to negative a7 minus b ax to the 7th, bx third plus cx. If I have this, then the relation between this is just plus 5. Gx equal to fx plus 5. So basically, gx without the constant term, it's an odd function. So basically, this portion going to be just a um, if we plus 5 on both sides, it's going to be 12. So gx g negative 7 is going to be 12. So basically, g7, because it's odd function, g7 just going to be negative 12. So g7 is negative 12, and then basically, the relationship between g and x, g is x plus 5 and f is g minus f. So basically it's going to be minus f, get back to negative 17. So this is just, a lot of function you're able to do it this way by using exploring oddity of the function. Okay, I think that's all for today. And um, hopefully you learn something. And it's just next week we're going to continue on other topic. But, just keep working on it. I'm going to assign a few more problems. Okay, have a nice one.